Welcome to our deep dive into aerospace materials. Today, we're exploring how advanced materials like superalloys, specialized aluminum alloys, titanium, steels, and even polymers come together to create engineering marvels in flight.
I'm really excited about this. So we're talking about materials that not only resist extreme heat and stress, but also involve really clever processing methods, right?
Exactly. These materials are designed to handle everything from the brutal temperatures inside rocket engines to the flexing wings of an airplane. It's
Yep.
they've got to be the ultimate multitaskers.
And what's truly fascinating is how each material's processing is meticulously tailored to its unique application. For example, those superalloys must be engineered to survive temperatures where normal metals would just, melt away.
Right. Those superalloys are our true titans of temperature. Essentially, they're designed to keep their strength, stability, and resist corrosion at insanely high temperatures. They come in three main flavors: nickel-based, cobalt-based, and iron-based, each one tailored for high endurance, wear resistance, or cost-effective strength.
And it's amazing to think that names like Hastelloy, Inconel, or even Rene aren't just fancy labels, but a promise of performance even when things get glowing hot.
Definitely. Now, if superalloys are handling extreme heat, then aluminum alloys are like the reliable workhorses of the aerospace world.
Yeah.
Their processing, whether wrought or cast, really changes the game. Wrought alloys go through processes like extrusion, forging, or rolling for higher strength. Cast ones, on the other hand, let us achieve intricate shapes we couldn't otherwise machine.
So it's sort of a trade-off. Wrought for strength and cast for shape complexity, right?
Exactly, and that's where the strengthening mechanisms come in. Think age hardening, strain hardening, and dispersion strengthening. It's like deliberately introducing defects to create sites for precipitates that block dislocation movement. In a way, it's like adding tiny roadblocks for flaws in the material structure.
Wait, so you're saying engineers intentionally create imperfections to make the overall material stronger? That's counterintuitive but brilliant.
Yes, it does sound odd at first, adding flaws to block other flaws. But when you consider how age hardening works, it's all about letting precipitates form at dislocation sites, which then stops them from causing catastrophic slip. It's a really clever interplay of structure and chemistry.
Moving on from metals, can we talk about titanium and steels? They seem almost indestructible, but are processed in very complex ways.
Absolutely. Titanium is remarkable for its strength-to-weight ratio, but once you mine it, you have to refine it using the Kroll process and then proceed through multi-stage melting, like triple melting, including VAR, to achieve that level of purity essential for jet engine parts. That eliminates minute flaws that could spell disaster.
And steels, especially miraging steels and high-grade stainless steels, also go through rigorous treatment. They're engineered to combine high strength with fracture toughness. But their usage is sometimes limited by things like brittleness at cryogenic temperatures, isn't it?
Exactly. Maraging steels are amazing for their combination of strength and toughness, while nickel-chromium steels endure harsh, high-temperature conditions. Engineers even categorize stainless into martensitic and austenitic types for different applications, one optimized by heat treatment and the other by cold working. It's all about finding the right fit for the job.
Now, one material that really surprised me is copper. I mean, when you think aerospace, copper isn't the first thing that comes to mind, right?
Precisely. But copper-based alloys, like Narloy Z or GR-Corp 84, are essential for thermal management in rocket engines. They excel at transferring heat away from critical components, which is vital to prevent catastrophic overheating. There's also copper alloys used in bearings and in sensitive instruments, where non-magnetic properties are crucial, like in beryllium copper.
It's like these alloys are the unsung heroes, quietly keeping everything cool and safe.
Exactly. While even the strongest metals have their limits, engineering isn't just about raw strength. Damage tolerance is a critical property where a material's ability to handle micro cracks and minor defects can mean the difference between safe operation and sudden failure. This involves analyzing fracture toughness, yield strength ratios, and crack growth rates under cyclic loads.
And man, the notion of hydrogen embrittlement really adds a layer of complexity. Hydrogen atoms subtly altering a metal's internal bonds is like a hidden assassin, weakening the structure over time.
Exactly. Hydrogen embrittlement is a silent threat. It drastically reduces fracture toughness by infiltrating the atomic lattice and changing that shared electron density. Materials like Ti6Al4V and certain nickel superalloys can suddenly go brittle, often near room temperature. It's a major, almost insidious risk that